Hello, class. We are going to continue with chapter 2.3, continuing on our set theory journey. Today we will be looking at Venn diagrams and set operation. Our objectives today are to understand the meaning of a universal set, understand the basic ideas of a Venn diagram, use Venn diagrams to visualize relationships between two sets, find the complement of a set, find the intersection of two sets, find the union of two sets, perform operations with sets, determine sets involving set operations from a Venn diagram, understand the meaning of and or, and use the formula for the cardinality of A union B. So, first, let's look at universal sets and Venn diagrams. The definition of the universal set is a general set that contains all elements under discussion. John Venn, born in 1843, died in 1923, created Venn diagrams to show the visual relationships among sets. The universal set is represented by a rectangle. Subsets within the overall universal set are depicted by circles, or sometimes ovals or other shapes. If we look at this visual representation up here in the right-hand corner, this rectangle is the universal set represented by U here. A is a subset within this rectangular universal set, and this A with an apostrophe here is the opposite of A, also known as what we will learn to be called the complement of A as we continue the lecture. Let's look at example 1. Determining sets from a Venn diagram. We want to use the Venn diagram to determine each of the following sets. Let's look at the set U, which is the universal set containing everything. The set U, if we're looking at our picture here, it contains the $sign, the M, the 5. It also contains this big set A, which in of itself contains this square and this triangle. So how would we write this? The way we would write this is we would include all the individual elements, the square and the triangle, the $sign, the M, and the 5. We would not include the set A because the set A is initially already included in here by including the set elements, the square and the triangle. So the universal set U here is once again, the square, the triangle, the $sign, the M, and the 5. The set A, which is a smaller set within the universal set, contains the two elements, the square and the triangle. The sets of elements in U that are not in A. Okay, let's look at this for part C. The set of elements in U that are not in A. What are in U but not in A? The ones that are in U but not in A are right here. The $sign, the M, and the 5. They are in U, but they aren't in A. So, let's list those. They would be written in roster notation, $sign, M, and 5. Simple enough. So, let's represent two sets in a Venn diagram. If we're looking at two disjoint sets, which is exactly how it sounds, it's two sets that have nothing in common. So no elements in common. They're disjointed. They are not jointed. Dis means not. Not jointed. Disjointed sets. So if we look at the disjointed sets here, A and B are disjoint. They don't have anything in common. If we look at a visual representation of proper sets, all elements of set A are elements of set B. So here, A is a proper subset of set B because A is completely contained in B, but A is not equal to B. Remember, that is the definition of proper subset. Equal sets. If A equals B, then A is a subset of B and B is a subset of A. Here, A and B are just that same circle in the inside of our universal set U. So they're the same thing. That's pretty simple. Sets with some common elements. If set A and set B have at least one element in common, then the circles representing the sets must overlap. And that overlap will contain the common elements. So the common elements here are just like this says. Right here in this region contain the common elements of sets A and B. So let's use the Venn diagram to determine what all is contained in the universal set U. Well, the universal set U contains all of the elements within here. Okay, that includes A, B, C, D, E, and F. We also want to know what the set B includes. Well, the set B here includes this D element and this E element. Now these 1, 2s, and 3s, all they're doing is indicating the area here, so they're not actual elements of the set. Maybe that's a poor representation here, but these themselves aren't actual elements. They're just indicating the particular areas that we're going to be looking at. Okay, so don't necessarily worry about them. They are not actual elements here of these sets. They are just basically headings or titles here. The actual elements themselves are these little letters. The set of elements in A but not in B. So we want the sets of elements in A but not B. That would include A, B, and C. D would not be included here because that element is shared with B. We want the elements that are just in A but not in B. Let's look at the set of elements in U that are not in B. Okay, we want the set of elements that are in U but not in B. Basically, we want to exclude everything in B then. We want to exclude the D, we want to exclude the E, but we want to include everything else. So we would definitely include F and G. That's easy. But we would also include A, B, and C. So this element set would be A, B, C, F, and G, because those are all the elements that are not in B that are contained in the universal set U, which is the overall rectangle. Let's look at the set of elements in both A and B. They only have one shared element. That is that middle D right here. That is the only shared element in our set. Now, I mentioned this earlier, but let's put a formal definition to it. Let's look at the complement of a set. The definition of the complement of a set is the complement of set A is symbolized by a complement using this symbol right here. Okay? A complement is the set of all elements in the universal set that are not in A. This idea can be expressed in set builder notation as follows. A complement equals X such that X is an element of the universal set and X is not in A, or is not a set or element of A. X is not an element of A, therefore it's an element of a complement. The shaded representation in this region is the complement of set A, or a complement. This region lies outside of the circle, that circle being A. So basically, a complement is anything outside of that circle A. Let's find the complement of a set. So finding a set's complement. We want to let the universal set be 1, 2, 3, 4, 5, 6, 7, 8, 9. And we want A to be the set 1, 3, 4, and 7. So you can see that 1, 3, 4, and 7 are contained in this set A, while these other elements that are not in A are just floating around out here in this universal set. The 2, the 5, the 6, and the 8. So in order to find the A complement, We're just looking for all the elements that are not in A. Therefore, A complement would be, oops, click too quick. A complement would be that 2, 5, 6, 8, and 9. So the set A complement contains all the elements of the set of the universal set that are not in the set A. Because set A contains the elements 1, 3, 4, and 7, these elements cannot be members of set A complement because they're already in A, which only leaves those elements we discussed, 2, 5, 6, 8, and 9, which I think can very easily be seen by the visual representation here. Next, we will look at the intersection of sets, where they intersect. The definition of the intersection of sets is the intersection of sets A and B, written A intersect B, is the set of elements common to both set A and set B. This definition can be expressed in set builder notation as follows. A intersect here is represented by this symbol here, which is almost like an N for intersect. So A intersect B equals X such that X is an element of A and X is an element of B. So let's find the intersection of two sets. Find each of the following intersections. The first set here is 7, 8, 9, 10, 11. And we want to intersect that set with 6, 8, 10, 12. I think you can see by the highlights here that the elements that they're sharing in common, which is their intersection, is 8 and 10. Now if I look at B, B is the set 1, 3, 5, 7, 9. And we can look at the intersection of that with 2, 4, 6, and 8. Now, what we initially notice is they share no common elements. If you have a situation where something shares no common elements between sets, your answer is the empty set. Because remember, sneakily, in all sets is the empty set. So all sets will share something, and that will be the empty set, if nothing else is to be shared. C, I have the set 1, 3, 5, 7, and 9, and I want to intersect that with the empty set. Following from B, we could tell that there's nothing in these sets that really have in common except the empty set itself, because the empty set lies in all sets. It's just known to be there. Now, we defined the intersection of sets. Now let's look at the union of sets. The union of sets A and B, written A union B, is the set of elements that are members of set A, or of set B, or of both sets. The definition can be expressed in set builder notation as the following. A union B, and like I said, I'll show you right here, this U stands for union. A union B equals X such that X is an element of A or X is an element of B, which means either or. Doesn't have to be both. It can be either or. So we want to find the union of these two sets. I have the set 7, 8, 9, 10, 11 unioned with 6, 8, 10, and 12. I'll keep in the back of my mind here that I'm basically combining these sets, and when doing so, I do not have to write each element more than once. So, when doing this, I will do it here. If I'm going to write this out by hand, the first set has a 7, the second set has an 8, along with the first set. So I've taken care of these elements. I've got a 9. What did I leave off? I've already left something off. I already left off a 6 to start with, because this one had a 6. That's why it's important to go through and check through your program. I also have a 9. I have a 10, but that's taken care of in both, but I only have to write it once. I have an 11, and I have a 12. So the union of these two sets is everything in both sets more clearly typed out here, 6, 7, 8, 9, 10, just as what we wrote. But we do not have to repeat the 10 or the 8. We just have to make sure it's in there at least once. Unions. Everything in both sets. So let's union this next set. 1, 3, 5, 7, 9, union with 2, 4, 6, 8. When we do that, we'll notice that our new union set is 1, 2, 3, 4, 5, 6, 7, and 8. Each element of both sets, all combined into a new set. If I union this set, 1, 3, 5, 7, and 9, with the empty set, I just get the original first set. Because the empty set is known to be in each set, so it doesn't even need to be written. The empty set in intersection and union. The empty set in intersection and union for any set A intersect the empty set is the empty set, and A union the empty set is just A. So what we see here is that for intersection, it takes it down to the empty set. For the union, it leaves the set alone and allows it to be itself. We need to look at performing some of these set operations. So, some problems involve more than one set operation. The set notation specifies the order in which we perform these operations. Always begin performing any operations inside of parentheses. It's just like PEMDAS. Parentheses, exponent, multiplication, division, addition, subtraction, as we would use in normal algebra. We will also make sure to take care of the parentheses first in these set operations. Example 6, performing these set operations. Given that the universal set U here equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the set A is 1, 3, 7, and 9, and the set B is 3, 7, 8, and 10, we want to find A union B complement. So, what I suggest doing here, we want the opposite of A union B. To me, the easiest way to find the opposite of A union B is to first find A union B. If I find A union B, that's all elements in A and in B, I see that that is 1, 3, 7, 8, 9, and 10. Remember, I do not have to repeat if the number shows up twice, like 3 shows up twice and 7 shows up twice. But I have 1, 3, 7, 8, 9, and 10. That is my set of A union B. For A complement or A union B complement, the opposite of this, I can go to my union or my universal set here and cancel all these elements of A union B out. So I'm going to cancel out 1, 3, 7, 8, 9, and 10. Everything left over is A union B complement. So that is the set 4, 5, 6, and I forgot that too. So you need to go through and make sure you check them all off so you don't skip one. Remember, order doesn't matter in sets. So when we click through here, we can see that our solution by the book would do just like what I said. It would list all the elements of the set A union B, and then it would find A union B complement. Now they right there is in order, but remember, sets don't necessarily have to be in order. They just have to contain all the correct elements. So on my set that I wrote and its set that it wrote are indeed the same thing because they contain the same elements. Let's look at the next example. Performing set operations continued. So we're going to look at this same group of sets here, the universal set, set A, and set B. Now we want to find A complement intersect B complement. The way I'm going to do this is I'm going to find A complement first. So let's find A complement, see what A complement is. A complement is basically the opposite of A. So I'm going to go through here and mark off what is in A so that everything else can be A complement. A complement should be 2, 4, 5, 6, 8, and 10. Next step is I'm going to find B complement. Now that means I'm going to go through here. I'll get rid of the scratches on the A's that I just scratched out, or you could even, still a step better, let's actually use the eraser and erase it so that we can go through here and figure out what B complement will be. I'll even write it in a new color. B complement. If I look at the elements of B, I'll mark those out. 3, 7, 8, and 10. That means that B complement should be 1, 2, 4, 5, 6, and 9. So we have A complement written out and B complement written out. Now we need to look at the intersection of those two. Okay, let's look at the intersection of A complement and B complement. What do they have in common? I'm going to use a different color for this as well. Let's use a red. Well, I do see that they both have a 2 in common. They both have a 4 in common, a 5 in common, a 6 in common. So, A complement intersect B complement should equal the set 2, 4, 5, and 6. And if you follow this work, you'll see that we are indeed correct on all fronts. The answer here, A complement intersect B complement, is indeed 2, 4, 5, 6. Now let's determine sets from a Venn diagram. We have the universal set here. A includes pi and E. The intersection of A and B is the square root of 2 and the square root of negative 1. And the set B itself, just by itself, is also E raised to the pi I, 10 raised to the 100, and 2 raised to the natural number sub 0. And outside here we also have a 666 floating around. And we want to use the diagram to determine each of the following sets. We're looking at A union B complement, A intersect B, A intersect B complement, A complement intersect B, A union B complement. Okay. So, let's look at the first one, A union B. That is the set of elements in A or B or both, which is basically everything in the highlighted blue region here. It includes regions 1, 2, and 3. All these numbers in A and B. So it includes pi, E, square root of 2, square root of negative 1, E raised to the pi I, 10 to the 100th, and 2 to the n naught. So if we wrote that in roster form, it's right there lined up with A. If I'm looking at A union B complement, it's basically everything that's not in A union B. So everything not in this shaded blue area. The only thing not in that shaded blue area is the 666. If I look at C, A intersect B, I'm basically looking at just this intersection point that they share here. That only contains 2 elements, the square root of 2 and the square root of negative 1. Okay. If I look at A intersect B complement, that's basically everything except what's in that middle section. So that includes pi E, E to the pi I, 10 to the 100th, 2 to the n naught, and the 666. If I look at A complement intersect B, so what is not in A intersect with what's in B, I'm strictly looking right here. Because these, oops, got a little a little off with my marker here. Let's try to make it a little bit better. As I said, I'm just looking at what's outside of A, but also in B, which includes this section right here, which is why we have e to the pi I, 10 to the 100th, and 2 to the n naught. If I look at A union B complement, so A union B complement, because I'm unioning these two sets, let me erase so we can draw it out piece by piece. I need to union everything in A along with everything in B complement. So I'm going to start out by circling everything in A. This is everything in A. And I'm going to union that with everything in B complement. Okay? So everything in B complement, I'll draw it in a slightly different color. B complement is everything outside of B. So basically includes this entire region except for inside that B. That's why we're going to have pi e square root of 2, square root of -1, and then also this 666. Let's look at sets and precise use of everyday English. Set operations in Venn diagrams provide precise ways of organizing, classifying, and describing the vast array of sets and subsets we encounter every day. Or, using this word or, refers to the union of sets. Using the word and in common everyday English means that we are looking at the intersection of sets. Now, if we look at the cardinal number of the union of two finite sets, the formula for the cardinal number of the union of two finite sets is the cardinal number of A union B equals the cardinal number of A plus the cardinal number of B minus the cardinal number of the A intersection B. So we've got the number of elements of A or B is the number of elements in A plus the number of elements in B minus the number of elements in A and B. And we have to subtract out that union because technically it's added twice. Let me do a visual representation to show you what I mean. Let me start with blue. If this is our A circle, and this is our B circle. If I add A plus B, then I have added this A once. I have added this B once. And what you'll notice is I've added this intersection portion twice, which is why I have to subtract that intersection portion off once. So that I'm only adding that intersection portion one time instead of twice. Example 8, the cardinal number of the union of two finite sets. Some of the results of the campus blood drive survey indicated that 490 students were willing to donate blood. 340 students were willing to help serve a free breakfast to blood donors. 120 students were willing to do both. How many students were willing to donate or serve breakfast? Okay, so we need to determine the cardinality of A union B. We need to look at the number of blood donors or breakfast donors. So we're going to look at the cardinality of blood donors or breakfast servers. And we could break that down with that formula we had. It equals the number of blood donors plus the number of breakfast servers minus the number of blood donors and breakfast servers. Basically the repeats there. Okay, so the way we look at this is we are looking here at the number of blood donors, that was 490, the number of breakfast servers, you can go back and check it if you want to, but it was 340, minus this intersection here of blood donors and breakfast servers, because they've been counted twice essentially. If you were to look at it here, that would be your final answer, right? But if you were to look at it, and I'll go through that in just a second, if you were to look at it in terms of a Venn diagram, so this will be your number of blood donors this would be the number of breakfast servers if you put these two numbers together, this 490 would be the entire circle of blood donors, including the intersection. This 340 would be the entire circle of breakfast servers. And remember, they share 120 here in the middle. But this 120 is included. It's included in the 340 and it's also included in the 490. So when you add 490 and 340, you've essentially added 120 in twice. And you don't want to do that. That's why we have to subtract it off here one time. Now, if we do this basic math here, we add 490 plus 340, we get 830. We subtract that 120, we see that there were 710 students that were willing to donate blood or serve a free breakfast overall. That's the total number of students. Now, some of them were willing to do more than one thing. There was 120 that were willing to do more than one thing. But there are only 710 students overall to pull from. I hope you understand, and I hope you enjoyed this lecture. Please go on your My Math Lab and try the homework associated with Chapter 2.3. If you have any questions or concerns, please don't hesitate to reach out to me via email so that I can help you. Other than that, I hope you've enjoyed learning today. Have a good rest of your day and a good afternoon. I will see you next time. We do have a test poised for after this lecture, test 1, for the Fall 2023 course. If you are taking this course at a different time, it could be different. Check with your professor and see. Otherwise, good luck on your first test and on your homework. If you need to, please reach out to me. I will be available. Have a good afternoon.